When I first began studying black holes, I carried with me a simple and dramatic image. A cosmic monster tearing through space, swallowing anything unlucky enough to wander too close. Like many people, I imagined black holes as engines of destruction, the universe's way of erasing stars, planets, and even light itself. It felt intuitive. After all, if nothing can escape them, surely nothing survives them either. What surprised me most was how incomplete that picture was. Black holes do not roam the universe hunting for matter. They do not drain galaxies or pull everything inward like a cosmic vacuum cleaner. In fact, most of the time, black holes are remarkably quiet. They sit where they formed, influencing their surroundings in subtle, almost elegant ways. The destruction we associate with them is not their defining feature. It is a side effect of very specific circumstances. This realization forced me to slow down and rethink what a black hole actually is. At its core, a black hole is not an object in the traditional sense. It is a region of space where gravity becomes so intense that escape is no longer possible. That distinction matters. Gravity does not suddenly switch on at the edge of a black hole. From far away, a black hole behaves like any other object of the same mass. If our Sun were somehow replaced by a black hole of equal mass, the planets would continue orbiting almost exactly as they do now. Earth would not be pulled inward. Seasons would still pass. Life, at least gravitationally, would continue uninterrupted. That fact alone shocked me. The danger of a black hole lies not in its presence, but in proximity. Only when matter comes extremely close does the true strangeness begin to reveal itself. The boundary we often hear about, the event horizon, is not a physical surface. There is no solid edge, no glowing wall, no visible line in space. It is a mathematical boundary defined by the point at which escape becomes impossible. Cross it, and every possible future path leads inward. Yet even here, the story is more subtle than destruction. From the perspective of a distant observer, nothing ever truly crosses the event horizon. Objects appear to slow down, stretch and fade, their light growing weaker and redder as time itself seems to resist their fall. The universe does not show us destruction in a single violent moment. It reveals it gradually, reluctantly, as though even spacetime hesitates to give up what it holds. This tension between appearance and reality became one of the most surprising themes in my study of black holes. They challenge not only physics, but intuition. What happens depends entirely on where you stand and how you observe. For someone falling toward a black hole, the experience would feel very different from what an external observer sees. Time would flow normally, at least at first. There would be no sudden signal announcing the crossing of the event horizon. No alarm, no visible boundary. Just a quiet, irreversible step into a region where the future narrows to a single direction. And yet, even then, destruction is not immediate. Popular culture often shows black holes shredding objects instantly, pulling them apart in moments. In reality, for very large black holes, an infalling observer might cross the event horizon without noticing anything unusual at all. The tidal forces, the stretching effects of gravity, can be surprisingly gentle at that boundary. The true violence occurs much deeper inside, near the center, where our current understanding of physics begins to break down. This realization surprised me more than any other. Black holes are not defined by chaos, but by precision. Their behavior follows exact mathematical rules. Their structure emerges naturally from Einstein's equations, not from cinematic imagination. They are extreme, yes, but not reckless. Even the material around black holes often survives longer than expected. Accretion disks, the glowing rings of gas and dust spiraling inward, can exist for millions of years. Matter does not vanish instantly. It heats, compresses, radiates energy, and follows paths dictated by gravity and angular momentum. In many cases, black holes are not destroyers of structure, but creators of some of the brightest objects in the universe. Quasars, among the most luminous phenomena known, are powered by matter falling toward black holes, not by matter disappearing into them. In that sense, black holes give more than they take, at least for a while. The deeper I looked, the clearer it became that black holes are not anomalies. They are natural outcomes of gravity pushed to its limits. Stars live, stars die, and under the right conditions, gravity wins. What remains is not a scar in the universe, but a new kind of order. One that forces space and time into unfamiliar shapes. What truly surprised me was how calmly the universe accepts this outcome. There is no cosmic alarm when a black hole forms, no announcement. The universe continues expanding, galaxies continue evolving, and stars continue shining. Black holes coexist with everything else, woven into the same cosmic fabric. Some galaxies even depend on them. The supermassive black holes at galactic centers appear to regulate star formation, shaping the growth and structure of entire galaxies over billions of years. Destruction, it turns out, is only one chapter in a much longer story. Studying black holes changed the way I think about endings. I used to imagine them as final points, places where matter, information and meaning are erased. But modern physics paints a more ambiguous picture. Questions about whether information is truly lost remain open. Some theories suggest it may be preserved in ways we do not yet understand, encoded in subtle correlations or released slowly over unimaginable timescales. If that is true, then black holes are not graves. They are vaults. This realization honestly reframed my entire understanding of them. Black holes are not violations of the universe's rules. They are, in fact, expressions of those rules taken to their extreme. They show us what gravity can do when absolutely nothing stops it. They reveal the limits of our theories and, well, invite us to push further. What surprised me most was not their power, but actually their restraint. Black holes do not destroy everything they touch. They do not unravel the universe. They sit patiently, shaping space-time with this quiet authority, just waiting for matter to come to them rather than, chasing it down. Their existence reminds us that the universe is not driven by drama, but by consistency, by laws that hold even in the darkest places. In trying to understand black holes, I expected honestly to confront chaos. Instead, I found structure. I expected violence, but discovered balance. I expected destruction, but encountered a deeper form of order. One that does not care about our fears or metaphors, only about the simple, relentless logic of gravity. This was the first surprise, and really it was only the beginning. One of the most persistent images I carried before studying black holes was the idea that they endlessly consume everything around them, stars, planets, even entire galaxies, pulling matter inward with unstoppable force. The phrase, "nothing escapes a black hole," made it feel inevitable, as if space itself were being drained towards some cosmic sink. What surprised me was how wrong that image is. Black holes do not hunt. They do not sweep through space, swallowing whatever crosses their path. In fact, a black hole's gravitational influence behaves no differently from that of any other object with the same mass. Gravity does not become more aggressive simply because an object has collapsed into a black hole. It obeys the same inverse square law it always has, weakening with distance in a predictable way. This means something deeply counterintuitive. From far away, a black hole is indistinguishable from a normal star of equal mass. If a star were to collapse into a black hole without losing mass, the orbits of nearby planets would remain unchanged. They would not spiral inward. There would be no sudden pull, no cosmic tug-of-war. Space would not rearrange itself in panic. Gravity does not announce the presence of a black hole. It simply continues doing what it has always done. This realization forced me to confront how much of our fear comes from language rather than physics. The word black hole itself sounds predatory. It implies emptiness, absence, consumption. But in reality, black holes are extraordinarily compact, not infinitely hungry. Their influence is local. Only objects that venture extremely close are at risk of crossing the event horizon. Most of the universe exists at safe distances, governed by the same gravitational rules that shaped it long before any black hole formed. So, why do black holes have such a fearsome reputation? The answer lies in how matter behaves when it falls toward them. When gas, dust, or stars come close enough, they do not fall straight in. Instead, they spiral. Angular momentum forces matter into disks that rotate at incredible speeds. Friction and compression heat this material until it glows intensely, releasing enormous amounts of energy. This process can actually outshine entire galaxies, producing quasars and active galactic nuclei, some of the brightest objects ever observed. To us, it looks violent, but the violence comes not from the black hole pulling harder than usual, but from matter resisting its fall. The black hole itself remains passive. It does not reach outward. It waits. This distinction surprised me because it reframes black holes as reactive rather than aggressive. They respond to what comes near them. They do not initiate destruction. Most black holes spend the majority of their existence in silence, surrounded by emptiness, barely interacting with their environment. Some may go billions of years without consuming anything at all. In that sense, black holes are among the most patient objects in the universe. Even supermassive black holes at the centers of galaxies do not consume their surroundings indiscriminately. Our own galaxy hosts one at its core, yet stars orbit peacefully around it, including those relatively close by, in cosmic terms. The Milky Way has existed for billions of years without being torn apart by its central black hole. If black holes were true vacuum cleaners, galaxies would not survive. This realization leads to an even deeper surprise. Black holes are not exceptions to cosmic order. They are products of it. They form when gravity overcomes all opposing forces, but once formed, they settle into predictable, stable relationships with their surroundings. They become anchors, not agents of chaos. You know, I also learned that the most dangerous region around a black hole is not the black hole itself, but actually the environment created by falling matter. Jets of high-energy particles can be launched along magnetic fields at, well, near light speeds, and these jets extend far beyond the black hole's immediate vicinity. Interestingly, these jets can influence star formation and even reshape entire regions of space. Yet again, the black hole is not acting alone. These phenomena really arise from interactions between gravity, motion, and magnetic fields. It's a complex dance rather than just a single act of destruction. This, honestly, forced me to question how often we confuse visibility with intent. We see the glow, the radiation, the extreme energy, and, well, we assume the black hole is actively doing something. In truth, much of what we observe is really the universe struggling to adapt to gravity under extreme conditions. The black hole is simply the stage upon which this struggle plays out. What surprised me most was just how ordinary black holes become once stripped of myth. They obey rules. They have limits. They do not expand endlessly. They do not pull from infinite distances. They do not violate the structure of space. They reshape it locally in ways that can be measured, predicted, and understood. Even the event horizon, often imagined as a deadly boundary, is not a destructive force in itself. It marks a limit of information, not an explosion of energy. Nothing special happens at that boundary from the perspective of physics alone. The drama exists mostly in our interpretation. This realization changed how I thought about danger in the universe. True danger is not always loud or obvious. Sometimes it comes from misunderstanding scale and distance. Black holes are dangerous only if you get very close, closer than most things ever do. The universe is vast, and black holes occupy tiny regions within it. The odds of encountering one by accident are extraordinarily small. And yet, despite their rarity, black holes have shaped the universe profoundly. They influence galaxy formation, regulate growth, and may even play a role in stabilizing cosmic structures. Far from being destroyers of order, they may be contributors to it. Their presence forces balance, controlling the flow of matter and energy over enormous timescales. This idea was deeply unsettling at first. I wanted black holes to be villains, singular threats that stood apart from the rest of physics. Instead, I found that they are deeply integrated into the universe's story. They are not mistakes or failures. They are natural outcomes, following the same laws that govern falling apples and orbiting planets. The vacuum cleaner metaphor collapses under scrutiny. Black holes do not clean space. They do not empty it. They exist within it, bound by the same geometry and rules as everything else. What surprised me most was not that black holes are powerful. That much was expected. It was that their power is so often misunderstood. Their influence is precise, limited, and contextual. They are extreme, but not chaotic. Silent, not ravenous. In learning this, I realized something broader about how we interpret the universe. We tend to project intention onto natural phenomena. We imagine hunger, aggression, destruction. But the cosmos does not think in those terms. It follows patterns, not motives. Black holes do not want anything. They do not consume out of need. They simply exist, and the universe responds accordingly. This was the second surprise in my study of black holes. That fear fades when understanding deepens. What once felt like a cosmic monster revealed itself as a quiet consequence of gravity. Not a vacuum cleaner, not a devourer, but, well, a reminder that even the most extreme objects obey simple rules. And with that realization, black holes became less terrifying and far more fascinating. Before I studied black holes closely, I imagined their edge as something sharp and unmistakable, a clear boundary where normal space ends and something dangerous begins. In my mind, the edge was almost physical, like a wall or a glowing rim marking the final limit. Cross it, and everything would immediately change. What surprised me was that the edge of a black hole is nothing like that at all. The boundary we call the event horizon is not a surface you can touch or see. It has no texture, no color, no thickness. It is not made of matter. It is a mathematical boundary defined by motion and time, not by substance. At that location, the geometry of space-time bends so extremely that all possible paths forward lead inward. Escape becomes impossible, not because something blocks the way, but because the way itself disappears. This distinction changed how I thought about boundaries in the universe. If you were falling toward a black hole, there would be no sign announcing your arrival at the event horizon. No shockwave, no sudden darkness, no invisible wall. If the black hole were large enough, you could cross that boundary without feeling anything unusual at all. Your body would remain intact. Your clock would tick normally, and the laws of physics would still seem familiar. At least for a while. That idea felt deeply unsettling. From far away, however, the story looks completely different. To a distant observer, you would appear to slow down as you approach the event horizon. Your movements would stretch in time, your image becoming dimmer and redder, as if the universe itself were reluctant to let you go. Eventually you would seem to freeze in place, never quite crossing the edge at all. Both perspectives are correct. This was one of the most surprising lessons I encountered. Black holes do not have a single absolute story. What happens depends on where you are and how you observe. Time itself becomes part of the experience, reshaping reality in ways that defy everyday intuition. The event horizon is not a place where destruction happens. It is a place where information changes how it can move. Once something crosses that boundary, it can no longer send signals back to the outside universe. Light, matter, and information are trapped not by force, but by geometry. Space-time tilts inward so completely that moving forward means falling deeper, regardless of direction. This was difficult for me to visualize at first. We are used to thinking of motion in terms of space: forward, backward, up, down. Near a black hole, motion becomes inseparable from time. Falling inward is not like being pulled down a well. It is more like being carried forward by time itself, with no alternative future available. What surprised me most was how quiet this transition is. Popular depictions show the edge of a black hole as violent or chaotic, but physics predicts the opposite. The true extremes occur deeper inside, where tidal forces stretch and compress matter in dramatic ways. The event horizon itself is simply a point of no return, not a point of destruction. This realization forced me to rethink what an edge really means. In everyday life, edges separate one thing from another: land from sea, inside from outside. The edge of a black hole does not separate two places in space. It separates two kinds of futures. On one side, multiple paths remain possible. On the other, the future narrows to a single outcome. That is a very different kind of boundary. Even more surprising is that the size of this edge depends entirely on mass. A small black hole has a tiny event horizon, while a supermassive black hole can have an event horizon larger than the orbit of entire planets. The physics at the edge is not inherently more dangerous for larger black holes. In fact, the opposite can be true. Larger black holes can be gentler at their boundaries, with weaker tidal forces. This overturns another common assumption, that bigger means more violent. In reality, the most extreme stretching effects occur near smaller black holes, not larger ones. A supermassive black hole's event horizon can be crossed smoothly, while a smaller one can tear matter apart long before it reaches the edge. This contradiction surprised me deeply. It revealed how poorly our instincts scale when applied to cosmic extremes. Size, danger, and violence do not correlate in simple ways when gravity dominates. The universe does not reward intuition, it rewards precision. The edge of a black hole is also not permanent in the way we might imagine. If a black hole gains or loses mass, its event horizon changes. The boundary grows or shrinks accordingly. It is dynamic, responsive, and shaped by the flow of energy over time. That fluidity made black holes feel less like objects and more like processes. Studying the event horizon taught me that black holes are not defined by what they contain, but by how they limit communication. The true significance of the edge lies in what cannot cross it outward, not in what crosses inward. This perspective transformed my understanding of cosmic limits. The universe is full of boundaries that are not physical walls, but informational ones. Horizons appear wherever observation meets limitation, not just around black holes, but in cosmology itself. The observable universe has its own horizon, beyond which light has not had time to reach us. In that sense, black holes are not anomalies. They are extreme examples of a much broader principle. We live in a universe defined not only by what exists, but by what can be known. That realization lingered with me long after I finished studying the mathematics. The edge of a black hole is not a place of spectacle. It is a place of silence, where the universe stops answering questions from the outside. And perhaps that is why it unsettles us so deeply. We fear edges because they mark the limits of understanding. The event horizon is not frightening because it destroys things, but because it hides them. It represents a boundary beyond which explanation falters and curiosity can no longer follow. What surprised me most was that the edge of a black hole is not dramatic at all. It does not announce itself. It does not glow or roar. It simply exists, a quiet line drawn by the geometry of space-time, separating what can be shared from what must remain unknown. In learning this, I realized that black holes challenge us not with violence, but with humility. They remind us that the universe does not owe us visibility or closure. Some truths lie beyond our reach, not because they are forbidden, but because the structure of reality itself sets limits. This was the third surprise, and it reshaped how I think about boundaries, not just in space, but in knowledge itself. Before studying black holes, I thought of time as something universal, a steady flow that moved forward at the same pace for everyone, everywhere. Seconds passed, minutes accumulated, and clocks agreed with one another. Even when I learned about relativity, time dilation felt abstract, something that mattered only at near-light speeds or in thought experiments. Black holes changed that understanding completely. What surprised me most was not that time slows near a black hole, but how deeply time becomes entangled with gravity itself. Near these objects, time does not merely tick more slowly. It behaves differently, reshaping the very structure of cause and effect. As an object approaches a black hole, its motion through space becomes inseparable from its motion through time. Gravity stretches time the way it stretches space, bending both into unfamiliar forms. To an observer far away, clocks near a black hole appear to run slower. The closer the clock is to the event horizon, the more pronounced this slowing becomes. At the edge itself, time seems to stop entirely. This idea was difficult for me to accept at first. How could time stop without everything freezing? The answer lies in perspective. For someone falling toward the black hole, their own clock continues ticking normally. Their heartbeat does not slow. Their thoughts proceed as usual. Time, from their point of view, remains intact. But to someone watching from afar, the infalling clock appears to slow endlessly, never quite reaching the event horizon. Time stretches, elongates, and fades into silence. Both experiences are real. This duality was one of the most unsettling aspects of studying black holes. Time is not absolute. It belongs to the observer. Gravity does not simply pull objects inward. It reshapes the flow of time itself, creating multiple equally valid versions of reality. What surprised me even more was how this behavior alters the meaning of before and after. Near a black hole, time and space swap roles in subtle ways. Outside the event horizon, you can choose where to go in space, but time always moves forward. Inside the event horizon, the situation reverses. Moving inward becomes as inevitable as moving forward in time. The singularity lies not in a direction you can avoid, but in a future you must reach. This reframing was profound. It suggests that falling into a black hole is not like traveling toward a place. It is like traveling toward a moment. The center of the black hole is not somewhere you might reach. It is something you will reach, just as tomorrow inevitably follows today. This realization blurred the distinction between motion and destiny. I had always thought of gravity as a force acting across space, pulling objects together. Near a black hole, gravity becomes something more fundamental. It dictates how time itself unfolds. It decides what futures are available and which are forbidden. This gave black holes a strange authority over causality. Events near the event horizon are stretched so thin in time that, from the outside universe, they never fully conclude. Information appears suspended, lingering at the edge of existence. This creates deep questions about how the universe preserves information and whether time itself can truly end. Studying these questions made me realize how incomplete our understanding still is. Einstein's equations predict time dilation with astonishing accuracy, but they also point toward regions where those equations fail. At the center of a black hole, time as we understand it may lose all meaning. Our current physics cannot describe what happens there. Concepts like before and after may simply cease to apply. That uncertainty surprised me more than any mathematical complexity. Black holes are not just objects that bend space. They are laboratories for testing the limits of time. They reveal how fragile our assumptions are, how dependent our experience of reality is on environment and scale. Even far from black holes, we see echoes of this truth. Time passes differently for satellites than for people on Earth. Gravity subtly alters every clock in the universe. Black holes simply amplify these effects until they become impossible to ignore. This realization changed how I thought about time in everyday life. Time is not a universal river flowing at a constant rate. It is a landscape shaped by mass and energy, with slopes and curves that vary from place to place. Near a black hole, that landscape becomes so steep that time nearly stands still, at least from some perspectives. What surprised me most was how calmly the universe accommodates this complexity. There is no contradiction in multiple versions of time coexisting. The universe does not insist on a single story. It allows reality to depend on where you are and how you move. Truth becomes local, not global. This idea was both unsettling and liberating. It suggests that certainty is a luxury of limited perspective. When we move beyond familiar environments, our definitions must evolve. Black holes force us to confront this necessity, showing us that even time, the most basic measure exists nå, is lesisches nen sal nundan maturan indan imainen numerus to tanchastus Hadal ke cons andersen de feiser amades verlisto setond. Studying time near black holes taught me that reality is far more flexible than we imagine. It bends, stretches and adapts, following rules that are consistent but deeply counterintuitive. The strangest part is not that time behaves oddly near black holes. It is that it behaves exactly as the laws of physics predict, and that those laws allow such behavior at all. This was the fourth surprise that time. Something we rely on to structure our lives is not a universal constant, but a participant in the cosmic story, shaped by gravity and woven into the fabric of space itself. And as I would soon learn, this entanglement between time and gravity leads to even deeper mysteries, ones that challenge our understanding of reality at its most fundamental level. Before studying black holes in detail, I assumed that their growth must always be dramatic, marked by explosive events, blinding radiation, and violent destruction. It seemed logical that something so extreme could only grow through chaos. I imagined black holes expanding by tearing stars apart in spectacular displays of cosmic violence. What surprised me was how often their growth is quiet. Many black holes gain mass slowly, almost gently, through a process that produces little light and attracts little attention. Matter can drift inward over vast periods of time, guided by gravity but not immediately destroyed. In these cases, the black hole does not announce itself with flares or jets. It grows in near silence, blending into the background of the universe. This idea challenged my expectations. When matter falls toward a black hole, it does not always crash violently into it. If the material has very little angular momentum, it can spiral inward efficiently, releasing minimal radiation. The energy escapes gradually, not explosively. From a distance, such a black hole might appear almost invisible, quietly increasing in mass while the universe carries on around it. This was surprising because it revealed how much of our understanding is shaped by what we can observe. The most famous black holes are the loud ones, those surrounded by glowing accretion disks, powerful jets, and intense radiation. These are the black holes that announce their presence across cosmic distances. But they are not the majority. Many black holes exist in a state of relative calm, growing slowly and steadily without dramatic signals. Silence, it turns out, is common in the universe. This realization made me reconsider how we define importance. Loud phenomena capture attention, but quiet processes often shape reality just as profoundly. Black holes that grow slowly may influence their surroundings over millions or even billions of years, subtly altering the evolution of galaxies without ever revealing themselves in spectacular ways. What surprised me most was how this quiet growth fits naturally into cosmic history. In the early universe, conditions were different. Gas was denser, temperatures were higher, and black holes had more opportunities to grow rapidly. Some of the first black holes likely experienced periods of intense activity, shining as quasars and reshaping their environments. But even then, these active phases were temporary. Over time, many black holes settled into quieter states. Growth does not have to be violent to be transformative. This pattern mirrors processes we see elsewhere in nature. Mountains rise slowly. Continents drift silently. Change does not always arrive with force. It often arrives through persistence. Black holes, despite their extreme reputation, follow this same principle. I also learned that black holes can grow by merging with other black holes, another process that is surprisingly subtle. When two black holes spiral together, the universe does not fill with light or sound. Instead, the merger sends ripples through spacetime itself, gravitational waves that pass through matter almost unnoticed. These waves carry energy away, allowing the black holes to settle into a single larger entity. From an electromagnetic perspective, the event may be nearly invisible. Only with specialized instruments can we detect these faint echoes of cosmic collisions. This was one of the most humbling realizations of my study. The universe does not always communicate in ways we can easily perceive. Some of its most dramatic events leave no visible trace. Black hole mergers, once thought to be purely theoretical, occur in darkness, announcing themselves only through subtle distortions of space-time. Quiet does not mean insignificant. The idea that black holes can grow without violence also reshaped how I thought about cosmic balance. Growth through gentle accretion and mergers allows black holes to integrate into their environments without disrupting everything around them. It creates a form of coexistence rather than domination. This balance may be essential to the long-term stability of galaxies. If black holes grew only through violent means, galaxies might be torn apart. Instead, the universe seems to favor moderation. Even at its extremes, it allows systems to evolve without constant upheaval. This restraint surprised me deeply. It suggested that the laws governing black holes are not reckless. They are precise, allowing for both dramatic and subdued outcomes depending on conditions. The same object can be both a source of intense radiation and a nearly invisible presence, depending on how it interacts with its surroundings. In studying this, I realized how misleading it is to define objects by their most extreme behaviors. Black holes are not always the monsters we imagine. Most of the time they are quiet participants in the universe's slow evolution. They grow not through constant destruction, but through patience and inevitability. This understanding shifted my perspective on scale and time. Human experience is shaped by short timescales. We notice explosions, sudden changes, dramatic events. The universe operates differently. It values duration over intensity. Black holes embody this principle, accumulating mass over eons rather than moments. What surprised me most was how natural this felt once I accepted it. There was no contradiction between the quiet growth of black holes and their extreme nature. Both are expressions of the same underlying laws. Gravity does not require drama. It requires only time. This realization softened my view of black holes. They became less like cosmic disasters and more like long-term processes, slow, persistent, and deeply woven into the fabric of cosmic evolution. In the end, studying how black holes grow taught me a broader lesson: that power does not always announce itself. Sometimes it works silently, shaping the universe over vast stretches of time without ever demanding attention. And that quiet influence may be one of the most profound forces of all. When I first thought about black holes, I assumed they were latecomers, objects that formed after stars and galaxies had already taken shape. It felt natural to imagine black holes as remnants, the final chapter in the life of massive stars, appearing only after long cosmic histories had already unfolded. What surprised me was learning that some black holes may be older than the galaxies that surround them. This idea initially felt backward. Galaxies, after all, are vast collections of stars, gas, and dust. How could something as extreme as a black hole exist before the structures that seem to define the universe itself? And yet, evidence increasingly suggests that some black holes formed astonishingly early, when the universe was still young and chaotic. In the first few 100 million years after the Big Bang, the universe was a very different place. Matter was clumped unevenly, temperatures were high, and the first stars were forming at incredible scales. These early stars were unlike those we see today. Many were enormous, short-lived and unstable, collapsing under their own gravity after brief but intense lives. Some of these collapses may have produced black holes far more massive than we would expect. What surprised me most was how quickly these early black holes appear to have grown. Observations of distant quasars, objects so far away that we see them as they existed billions of years ago, reveal black holes with masses millions or even billions of times that of our Sun, existing when the universe was less than 1 billion years old. By cosmic standards, that is almost instantaneous. This raises a profound question. How did they grow so fast? Traditional models of black hole growth struggle to explain this rapid accumulation of mass. There simply may not have been enough time for black holes to grow gradually through normal processes. This has led scientists to consider alternative possibilities, including the idea that some black holes formed directly from the collapse of massive clouds of gas, bypassing the star stage entirely. If this is true, then black holes were not just products of galaxies. They were participants in their formation. This realization changed how I viewed the relationship between black holes and the universe's structure. Instead of being consequences of cosmic evolution, some black holes may have been drivers of it. Their gravity could have helped gather matter, shaping the early environments where galaxies would later emerge. In this sense, galaxies may have grown around black holes, not the other way around. This idea felt almost poetic. It suggests that at the heart of many galaxies lies something ancient, an object that existed before the stars that now orbit it. A silent witness to the universe's earliest moments, shaping its surroundings long before light filled the cosmos in familiar ways. What surprised me was how this reframes cosmic history. We often imagine the universe assembling itself piece by piece, gradually building complexity. But the existence of early black holes hints at a more dynamic beginning, one where extreme objects appeared quickly, influencing everything that followed. Black holes, in this view, are not late-stage accidents. They are foundational. Even our own galaxy likely hosts a supermassive black hole that formed early in its history. While the stars of the Milky Way are diverse in age, its central black hole may have been present long before many of them were born, quietly shaping the galaxy's growth over billions of years. This longevity surprised me deeply. Black holes are often associated with endings, yet here they are at the beginning, enduring through nearly the entire history of the universe. They outlive stars, survive galactic collisions, and persist as stable structures while everything around them changes. They are among the most ancient objects we can study. This realization altered how I thought about time on cosmic scales. Human history spans thousands of years. Stellar lifetimes span millions or billions. Black holes bridge these scales, existing across almost the entire age of the universe, unchanged in essence, even as everything else evolves. What surprised me most was how little they need to do to have such a lasting impact. By simply existing, black holes influence the motion of matter, regulate energy flow, and shape the large-scale structure of galaxies. They do not need to be active or visible to matter profoundly. Their gravity alone is enough. This quiet endurance gives black holes a strange kind of authority. They are not rulers in the traditional sense. They do not command or act. They persist. And in persisting, they shape outcomes over immense spans of time. Studying this made me rethink how influence works in the universe. Power does not always come from action. Sometimes it comes from presence. Black holes exemplify this principle. Their age and stability allow them to anchor cosmic systems, providing continuity in a universe defined by change. In realizing that some black holes may be older than galaxies themselves, I felt a shift in perspective. These objects are not merely remnants of dead stars. They are ancient participants in the universe's story, witnesses to its earliest chapters and architects of its long-term structure. This was the sixth surprise in my study of black holes, that the darkest objects in the universe may also be among its oldest, quietly shaping the cosmos from the very beginning. Before studying black holes, I thought of light as the ultimate escape artist. Fast, untouchable, and always moving forward. Nothing, I believed, could truly trap light except by absorbing it completely. The idea that light itself could become caught in a kind of orbit felt impossible, almost contradictory. What surprised me was learning that light can circle a black hole. This realization reshaped how I understood gravity. We often think of gravity as something that pulls on mass, something that affects objects with weight. Light has no mass, yet near a black hole, gravity does not merely pull, it bends space itself. And light, which always follows the straightest possible path through space-time, ends up curving along with it. Near a black hole exists a region known as the photon sphere. Here, space-time is curved so extremely that light can travel in closed paths, looping around the black hole instead of escaping or falling inward. These orbits are fragile and unstable, but they exist, a strange balance between motion and gravity. The idea that light can orbit felt deeply unsettling. Light is our primary tool for understanding the universe. We rely on it to carry information across vast distances. To imagine it circling endlessly, trapped by geometry rather than force, made black holes feel even more alien. What surprised me most was how this phenomenon helps explain what we actually observe. The images of black holes we have seen are not pictures of the objects themselves. They are images of light that has been bent, stretched, and redirected by extreme gravity. The glowing rings captured by telescopes are formed by photons that have skimmed the edge of the black hole, some of them looping around multiple times before finally escaping toward us. In a sense, we are seeing light that has taken the long way around. This realization gave those images a new depth. They are not snapshots of matter, but records of space-time geometry. Each glowing arc represents a path light was forced to take by gravity's curvature. I found it remarkable that black holes reveal themselves not by emitting light, but by controlling its movement. This control does not come from intention or design. It is simply the natural outcome of gravity acting on space-time. The black hole does not grab light. It reshapes the paths light is allowed to follow. This distinction mattered to me. It reinforced the idea that black holes are not active agents, but environments, regions where the rules of motion take on extreme forms. Light behaves strangely not because it is being attacked, but because the space it moves through has been radically altered. What surprised me further was how precise these effects are. The radius of the photon sphere depends directly on the mass of the black hole. The equations describing it are exact, leaving little room for ambiguity. Even in such extreme conditions, the universe remains mathematically consistent. Chaos does not replace order, it coexists with it. This precision challenged my assumptions. I had imagined black holes as places where physics breaks down completely. Instead, I found regions where physics becomes more demanding, more exacting, but still deeply structured. The bending of light is not random. It follows strict geometric rules, allowing scientists to predict what we should see with remarkable accuracy. This is how we test our theories. By observing how light behaves near black holes, we can measure their mass, spin, and orientation. We can compare predictions with observations and refine our understanding of gravity itself. Black holes become tools, not obstacles, in the pursuit of knowledge. That role surprised me. Objects once thought to be unknowable now help us probe the limits of physics. Light, trapped briefly in orbit, carries information about regions we cannot directly explore. It becomes a messenger, whispering clues about the structure of space-time before finally escaping. There is something poetic about that. Even in the darkest regions of the universe, light finds ways to tell a story. It bends, loops, delays, but it does not vanish without leaving a trace. The universe allows us glimpses even when it denies us access. Studying the photon sphere made me reflect on perspective. What looks like an impossible trap from one viewpoint is simply a curved path from another. Light is not confused. It follows the geometry it is given. It is our intuition that struggles, shaped by flat spaces and weak gravity. Black holes expose those limitations mercilessly. They force us to abandon straight lines, simple paths, and comfortable assumptions. They reveal a universe where even light must adapt, surrendering its freedom to the deeper structure of reality. What surprised me most was how natural this all becomes once accepted. There is no violation of logic here, only an extension of it. Gravity bends space. Light follows space. Therefore, light bends. At extremes, that bending becomes dramatic enough to create orbits. Simple rules, astonishing outcomes. This was the seventh surprise in my study of black holes. That light, the symbol of freedom and speed, can be made to circle endlessly, guided by gravity's invisible hand. Not destroyed, not captured in violence, but held in a delicate, unstable balance. And through those looping paths, the universe allows us to see what would otherwise remain hidden. Before I learned how black holes merge, I imagined the event as one of the most violent spectacles in the universe. A collision marked by blinding flashes, explosive radiation, and chaos spreading outward in all directions. Two objects so massive coming together felt like it had to be dramatic in every possible sense. What surprised me was how silent the process truly is. When two black holes spiral toward one another and finally merge, there is often no light, no sound, and no visible explosion at all. From the perspective of traditional astronomy, the event can be completely dark. No telescope sensitive to light alone would notice anything unusual happening. And yet, something extraordinary occurs. As the two black holes orbit each other, they lose energy by disturbing the fabric of space-time itself. This disturbance travels outward as gravitational waves, ripples in space-time that stretch and compress reality as they pass. These waves move at the speed of light, carrying information about the masses, speeds, and shapes of the merging black holes. The universe speaks, but not in light. This idea surprised me deeply because it revealed how limited our senses are. For most of human history, we assumed that to observe the universe, we needed light. If something produced no light, it was effectively invisible. Black hole mergers shattered that assumption. They showed us that the universe has other ways of communicating. Gravitational waves are unimaginably subtle by the time they reach Earth. They change distances by less than the width of an atomic nucleus. Detecting them requires instruments of incredible precision, capable of measuring distortions smaller than anything we experience in daily life. And yet we have detected them. The first confirmed detection of gravitational waves was not just a scientific milestone, it was a revelation. It confirmed that black holes merge as predicted and that space-time itself is dynamic, capable of carrying energy across vast distances without the need for matter or light. What surprised me most was how clean these signals are. Unlike light, which can scatter, absorb, or distort, gravitational waves pass through matter almost unaffected. They carry information directly from the event, untouched by intervening gas, dust, or radiation. In a sense, they provide a more honest record of what happened. This gave black hole mergers a strange intimacy. Even though we cannot see them, we can feel their echo in the structure of space-time. The universe leaves a fingerprint, subtle but precise, allowing us to reconstruct events that occurred billions of years ago. The silence of these mergers also challenged my expectations about violence. Two black holes merging is one of the most energetic events in the universe, releasing enormous amounts of energy, not as light, but as gravitational waves. And yet, that energy does not manifest as destruction spreading outward. Space-time ripples and then settles as if the universe absorbs the event without protest. There is no debris, no shockwave, no aftermath in the usual sense. This calm resolution surprised me. It suggested that even at its most extreme, the universe prefers balance over chaos. Energy is redistributed, geometry adjusts, and stability returns. The merged black hole settles into a new, larger form, described by only a few properties: mass, spin, and charge. Everything else is forgotten. This idea that black holes erase complexity is both elegant and unsettling. No matter how complicated the original system was, the final result is simple. The universe moves from complexity toward minimalism. Studying black hole mergers made me realize how deeply different cosmic events are from human ones. We associate energy with noise, destruction, and visible change. The universe does not. It allows immense transformations to occur quietly, leaving behind only subtle traces for those who know how to listen. What surprised me most was that we had lived our entire history unaware of these events. Black holes were merging long before humans existed, sending ripples through space-time that passed through Earth unnoticed. Entire cosmic dramas unfolded in silence, their signals washing over our planet without consequence. Only now have we learned to listen. This realization made the universe feel both more alive and more indifferent. Alive because space-time itself responds to change. Indifferent because these events do not care whether we observe them or not. The universe does not perform. It simply happens. Black hole mergers taught me that observation is not limited to sight. Understanding requires new senses, new tools, and new ways of thinking. Light is only one language the cosmos speaks. This was the 8th surprise in my study of black holes, that some of the most powerful events in existence occur without spectacle, without illumination, and without sound, leaving behind only faint ripples in the fabric of reality. And through those ripples, we are learning to hear the universe in an entirely new way. Before I studied black holes in detail, I imagined them as static objects, dense spheres of darkness sitting silently in space. I thought of them as unchanging, unmovable, existing only to pull in matter with their gravity. The idea that they could spin, and spin incredibly fast, was something I hadn't fully appreciated. What surprised me was the extremes of this rotation. Some black holes rotate at speeds close to the speed of light. Their spin is not just fast, it affects the space around them in profound ways. Space-time itself becomes twisted, a phenomenon known as frame dragging. Imagine the black hole as a spoon stirring a thick, invisible cosmic soup. Everything nearby, gas, dust, even light, is forced to follow the swirl. This spinning changes the shape of the black hole's event horizon. A rapidly spinning black hole is not perfectly spherical. It bulges at the equator, flattens slightly at the poles. The faster it spins, the more extreme this deformation becomes. What surprised me most was that this spin can extract energy. A rotating black hole is like a reservoir of untapped rotational energy. In certain conditions, matter falling toward it can tap into this energy, launching jets of particles at nearly light speed. These jets can extend for thousands of light years, far beyond the black hole's immediate environment, shaping entire galaxies. It made me realize that black holes are not merely consumers. Some can redistribute energy, actively influencing the cosmos around them. The spin becomes a source of activity, not just an internal feature. Even the gravitational waves from merging black holes are affected by spin. If one or both of the black holes is spinning rapidly, the resulting waves carry distinct signatures, allowing scientists to measure rotation billions of light years away. The universe leaves clues, waiting for us to decode them. What amazed me was how delicate and precise the process is. Spin is limited. A black hole cannot rotate beyond a certain speed without violating fundamental physics. There are boundaries even in this extreme behavior. Rules governing how fast it can spin, how energy can be transferred, and how the surrounding space reacts. This insight transformed how I imagined black holes' interactions with their environments. A spinning black hole is not a passive sink. It sculpts nearby matter, channels energy into jets, and twists the very fabric of space-time. Its rotation is a form of cosmic communication, subtle yet profound. I also realized that spin is a historical record. A black hole's rotation reflects how it formed, whether from the collapse of a massive star, the accumulation of surrounding matter, or mergers with other black holes. Its spin tells a story about its past, frozen into its motion. What surprised me most was how elegant this process is. The universe allows extreme physics to operate in strict harmony. Spinning black holes follow precise mathematical rules, their rotation measurable and predictable, even under conditions that seem beyond imagination. The combination of mass, spin and charge, the three defining properties of a black hole, becomes a complete description of these objects. Everything else is irrelevant. Despite their complexity and the extremity of their behavior, black holes are, in a sense, beautifully simple. This was the 9th surprise in my study of black holes, that these mysterious objects, often imagined as chaotic and unknowable, can rotate at nearly unimaginable speeds, shaping their surroundings in ways both subtle and dramatic, yet still following the universe's fundamental rules. And through their spin, they reveal that even darkness has a rhythm, a motion, and a story to tell. Before studying black holes in detail, I assumed that the largest objects in the universe would be obvious, bright, massive, and impossible to miss. Galaxies announce themselves with light, stars shine, nebulas glow, but black holes can be enormous and still almost completely invisible. This was one of the things that surprised me most. Some supermassive black holes have masses billions of times that of the Sun. Their gravitational influence is immense, shaping entire galaxies. Yet, if they are not actively consuming matter, they emit no light. You could pass them in space and never know they were there. Their presence is detectable only by observing the motion of nearby stars, gas and dust. The invisibility of these giants is counterintuitive. We equate size with visibility. A mountain is hard to miss. A planet can be seen across space. But gravity alone, no matter how strong, does not have color or brightness. The largest black holes quietly bend the universe around them, leaving a subtle signature rather than a spectacle. What surprised me even more was how this invisibility complicates our understanding of the cosmos. Some of the earliest discoveries of supermassive black holes came not from seeing them directly, but from observing their effects. Stars orbiting unseen points in space, gas swirling at incredible speeds, light being bent by gravity. These clues hinted at enormous hidden masses. The black hole itself remained invisible, yet its impact was unmistakable. This taught me an important lesson. Presence does not require visibility. Influence can be subtle, extending far beyond what we can perceive with our eyes. Black holes dominate their surroundings not with light, but with the unseen force of gravity. Even more surprising is how different types of black holes behave. Some stellar mass black holes, a few times the mass of the Sun, are detectable because they pull matter from a companion star, producing X-rays. Others, of similar mass, float alone and are essentially invisible. Size alone does not guarantee detectability. Activity does. This made me rethink how we search the universe. Observations must account for what cannot be seen, not just what glows. We are blind to much of the cosmos because gravity does not shine. Black holes teach us humility, that the universe contains more than meets the eye. I was also surprised by the scale involved. Supermassive black holes can have event horizons larger than the orbit of planets in our solar system, yet they remain dark. They are immense voids whose size is incomprehensible, but whose presence is only inferred through motion and geometry. Even when invisible, they affect the evolution of galaxies. Their gravity can stabilize orbits, guide the formation of stars, and influence how matter accumulates over billions of years. The universe is shaped by objects that remain almost entirely hidden. This invisibility adds an element of mystery. Unlike stars or galaxies that announce themselves, black holes require careful detective work to detect. They challenge our instincts, which are tuned to perceive light and motion. What surprised me most was the elegance of this hidden influence. The largest black holes can quietly govern entire systems, enforce cosmic structure, and shape the history of galaxies, all without ever being directly observed. Their power is measured not by visibility, but by effect. This was the 10th surprise in my study of black holes, that enormous, powerful and ancient objects can exist in near-total invisibility, influencing the universe in profound ways, yet remaining hidden from direct view. And in understanding this, I realized that sometimes the most significant forces are those we cannot see, only perceive through their consequences. Before studying black holes, I imagined that if a black hole encountered a star, the process would be slow and dramatic. A star being torn apart over time, like a cosmic tug-of-war. Movies and illustrations often show stars stretching and exploding as they approach. What surprised me was how efficiently black holes can consume stars. When a star wanders too close, tidal forces stretch it into a thin stream of gas. In extreme cases, the star can be disrupted almost instantly, its material drawn inward toward the black hole with astonishing speed. This is called a tidal disruption event. It is violent in the sense of forces involved, yet it can occur without visible chaos beyond the bright flare emitted as the stellar material heats up. The efficiency of the process shocked me. A single black hole can consume vast amounts of matter in a short time, yet the scale is invisible from most perspectives. A star that might seem immense from afar is reduced to streams of gas in moments. What surprised me most is how predictable the process can be. Astrophysicists can calculate exactly how close a star can approach before being torn apart. They can predict the flares, the energy released, and even the debris' behavior afterward. Despite the seeming chaos, the laws of physics remain precise. The bright flare that often results is caused not by the black hole itself, but by the friction and compression of gas as it spirals inward. The star's material heats to millions of degrees, shining briefly before crossing the event horizon and vanishing from view. The black hole itself remains dark. Only the process announces its presence. This realization made me rethink what eating means in the cosmic sense. It is not like a predator consuming prey for sustenance. The black hole does not digest or change. It simply absorbs, allowing gravity to reorganize the universe according to its rules. Another surprise is how this consumption affects the surrounding environment. The release of energy during tidal disruption can trigger star formation nearby, alter the motion of gas clouds, and even influence the dynamics of an entire galaxy. Destruction in one sense becomes creation in another. Studying these events taught me that black holes are both destructive and constructive. Their influence is subtle, yet profound. Even in devouring a star, they shape the universe on scales far beyond the immediate encounter. I was also surprised by the rarity and timing. Tidal disruption events are uncommon because a star must pass very close to a black hole. They are cosmic accidents, fleeting and unpredictable on human timescales. Observing one is like witnessing a sudden private drama that the universe rarely allows us to see. This rarity adds to the fascination. Each event is unique, providing a glimpse into the power and subtlety of black holes. It shows how even the most extreme objects in the universe operate under strict physical rules, producing results that can be anticipated but never fully controlled. What surprised me most was how quickly a star can disappear. From an observer's perspective, a star can approach, stretch, flare, and vanish in a matter of weeks or months. A blink of an eye, in cosmic terms. Yet, in that short span, it teaches us about gravity, energy, and the extreme limits of physics. This was the 11th surprise in my study of black holes, that black holes can consume stars whole, not with chaotic destruction, but with precise, efficient, and profoundly impactful processes that leave both destruction and creation in their wake. And in understanding this, I realized that black holes are not mere consumers of matter. They are active participants in the ongoing story of the universe, shaping everything around them, often in ways invisible to us. Before studying black holes, I thought of space as a static backdrop, a stage where stars, planets, and galaxies performed their cosmic dance. It seemed logical to imagine space as uniform, unchanging, and unaffected by the objects within it. What surprised me was learning that black holes can actually twist space itself. According to Einstein's theory of general relativity, mass and energy curve space-time. This effect becomes extreme near black holes, especially those that spin rapidly. The faster a black hole rotates, the more it drags the surrounding space along with it, a phenomenon called frame dragging. Imagine space as a thick, invisible fabric. A spinning black hole is like a stirring rod, twisting that fabric in its vicinity. This twisting can affect the orbits of nearby matter. Gas, dust, and even stars can be forced into unusual paths, following the contours of warped space rather than moving in straight lines. Light itself is dragged, changing the way we see objects near the black hole. What surprised me most was how far-reaching this effect can be. Frame dragging is not limited to the immediate edge of the event horizon. In some cases, it can influence the dynamics of entire accretion disks, guiding the flow of matter and shaping the formation of jets that extend for thousands of light years. The idea that space itself is being twisted was difficult for me to grasp. We are accustomed to thinking of space as empty and passive, yet here space is active, a participant in the black hole's influence, shaping motion, energy, and structure. Even light is affected. Photons moving near a spinning black hole can follow paths that curve and loop in ways impossible under ordinary circumstances. This bending of light contributes to the glowing rings we observe around some black holes, revealing the extreme geometry of space itself. What surprised me even more was the subtlety of the effect at distances. While the twisting is strongest near the event horizon, its influence fades gradually, showing that the geometry of space is continuously connected. There are no abrupt boundaries. The black hole's presence extends through space in a smooth, almost elegant way. This realization changed how I imagined the cosmos. Black holes are not isolated voids. They are sculptors of their surroundings. They shape trajectories, redistribute energy, and influence structure, all through the twisting of the invisible fabric of reality. I also found it fascinating that this twisting is measurable. Scientists can detect the effects of frame dragging by observing the precession of matter near black holes, or by studying the paths of stars orbiting supermassive black holes. These measurements confirm predictions made decades earlier. showing the universe's consistency even under extreme conditions. What surprised me most was how gentle the universe is in applying such extreme physics. The twisting of space is intense, yet it follows smooth mathematical rules. There is no chaos, only precise curvature and rotation that matter and light obey. Studying these effects taught me that space is not a passive container, but an active element of the cosmos. The universe is dynamic, flexible and responsive, even at scales we cannot perceive directly. Black holes reveal the fluidity of space itself, making the invisible structure of the cosmos tangible through motion and gravity. This was the 12th surprise in my study of black holes, that black holes can twist space, bending the invisible fabric of reality, guiding matter, light and energy along paths dictated not by force alone, but by the geometry of the universe. And in understanding this, I realized that space is not empty. It is alive, responsive, and intimately connected to the objects within it. Before studying black holes, I imagined them as permanent, unchanging, and eternal. Cosmic objects that once formed would last forever. Their immense gravity seemed like a guarantee of permanence. What surprised me was learning that black holes are not entirely eternal. They can slowly evaporate through a process called Hawking radiation, a theoretical discovery by Stephen Hawking in the 1970s. Hawking proposed that black holes are not completely black. Quantum effects near the event horizon allow tiny amounts of energy to escape as radiation. Over unimaginable spans of time, this radiation can cause a black hole to lose mass, shrink, and eventually vanish. This idea was profoundly unsettling at first. The thought that even objects as extreme as black holes have lifetimes challenges our notions of permanence. Nothing in the universe is truly eternal. Not stars, not planets, not even the darkest regions of space. What surprised me most was the subtlety of the process. Hawking radiation is extraordinarily weak for large black holes, so the effect is imperceptible for stellar mass or supermassive black holes. They would take longer than the current age of the universe to evaporate significantly. Yet the principle is universal. Every black hole, no matter its size, slowly leaks energy over time. This realization changed my perspective on cosmic impermanence. Black holes, which seem like the ultimate consumers of matter and energy, are themselves subject to decay. Even the most extreme objects have limits, and the universe enforces them patiently. Evaporation also creates deep philosophical questions. What happens to the information contained within a black hole as it disappears? Does the universe retain it, or is it lost forever? This puzzle, the black hole information paradox, challenges our understanding of physics, combining quantum mechanics, relativity, and thermodynamics in ways still unresolved. The idea that black holes could vanish taught me something surprising about time and scale. Processes we consider slow or negligible on human timescales, like erosion or decay, take on cosmic significance when applied to black holes. The universe operates on timelines far beyond our daily perception, yet even there, change persists. Another surprising aspect is the elegance of Hawking's theory. The radiation arises naturally from the interplay between quantum mechanics and gravity. There is no contradiction, only a subtle mechanism that allows energy to escape the most extreme gravitational wells. What surprised me most was the poetic irony of it all. Black holes, which consume everything around them, are themselves impermanent. They devour, dominate, and distort space-time, yet in the end They obey the slow, patient rules of the cosmos. Studying black hole evaporation revealed that even the universe's most formidable objects are part of a cycle, one of formation, transformation, and eventual dissolution. It reminded me that permanence is an illusion, and that even darkness is subject to the passage of time. This was the 13th surprise in my study of black holes, that these objects, which seem eternal and all-consuming, can evaporate, slowly returning their energy to the universe and leaving behind profound questions about the nature of reality, information, and time itself. And in understanding this, I realized that even the most extreme entities are not exempt from change, a humbling lesson about impermanence on the grandest scales. Before studying black holes, I imagined them as simple vacuum cleaners of the universe, objects that only pull matter inward, swallowing anything that comes near. I assumed that all their effects were inward-facing, destructive, and contained. What surprised me was learning that black holes can also produce some of the most energetic outflows in the universe: cosmic jets. These jets are narrow beams of charged particles that shoot outward at nearly the speed of light, extending for thousands, sometimes even millions, of light years. They are powered not by the black hole itself, but by the matter swirling around it in the accretion disk. As gas and dust spiral inward, magnetic fields twist and channel some of this energy outward, forming these spectacular jets. What amazed me was the scale. A single jet can stretch far beyond the host galaxy, influencing the intergalactic medium and even shaping the growth of neighboring galaxies. The black hole, which exists at the heart of a galaxy, can have effects that reach across cosmic distances. The precision of these jets also surprised me. Despite the chaotic environment near a black hole, the jets remain narrow, collimated, and highly directional. They are like cosmic lighthouses, piercing through darkness with extreme focus and energy. I was even more surprised by their impact on galactic evolution. Jets can heat surrounding gas, suppressing star formation in some regions while triggering it in others. They regulate the growth of galaxies, acting as both creators and regulators. In other words, black holes are not just destructive. They actively participate in the balance and development of cosmic structures. Another surprising aspect is the speed at which the jets move. Near the speed of light, they carry enormous energy, but they do not disrupt the black hole's immediate environment entirely. The process is extreme yet remarkably stable, guided by the geometry of magnetic fields and the dynamics of the accretion disk. What surprised me most was the contrast between the invisible black hole and the brilliant, visible jet. The central black hole may be hidden, dark, and impossible to see directly, yet its influence manifests as one of the most luminous and energetic phenomena in the universe. Light emerges not from the black hole, but from the environment it shapes. Studying these jets taught me that black holes are not simple consumers of matter. They are organizers, channels, and transformers of energy. They connect scales, from the immediate event horizon to the surrounding galaxy and beyond, bridging space in ways that are almost poetic. The elegance of the physics also amazed me. Magnetic fields, plasma dynamics, and gravity collaborate to create structures that are both immensely powerful and precise. The universe allows chaos to coexist with order, producing phenomena that are breathtaking in both beauty and scale. This was the 14th surprise in my study of black holes, that these objects, often imagined as dark, destructive, and inward-facing, can produce cosmic jets that shape entire galaxies, revealing that black holes are not only consumers of matter, but also powerful architects of the cosmos. And in understanding this, I realized that even in darkness, black holes can give rise to some of the universe's most luminous and far-reaching creations. Before studying black holes, I thought of time as absolute, the same everywhere in the universe, flowing uniformly like a steady river. I imagined that clocks on Earth would behave the same near distant stars or planets. What surprised me was how dramatically black holes can distort time. According to Einstein's theory of general relativity, the stronger the gravitational field, the slower time passes relative to areas with weaker gravity. Near a black hole, gravity is extreme, and time slows to an extraordinary degree. A clock close to the event horizon ticks far more slowly than a clock far away. This effect, called gravitational time dilation, is not theoretical fantasy. It is measurable. For someone orbiting near the event horizon, minutes could pass while years elapse for a distant observer. Time, which feels constant to us, becomes relative in the presence of extreme gravity. What amazed me most was the scale of this effect. Near a supermassive black hole, time dilation can be dramatic enough to make interstellar travel feel like a journey into a different temporal reality. The universe behaves in ways that challenge our everyday intuitions. The consequences for observation are profound. If matter falls into a black hole, distant observers see it slow down as it approaches the event horizon, appearing almost frozen in time. The black hole itself seems to act as a cosmic pause button, stretching moments into eternity from afar. I was also surprised by the philosophical implications. Time, which we perceive as linear and universal, becomes a local property, shaped by gravity and space. Near a black hole, the universe behaves differently, and our understanding of cause, effect, and duration is tested. Another surprising aspect is how this influences energy and motion. The slower passage of time near the event horizon affects the dynamics of accretion disks and the radiation emitted. It allows black holes to radiate energy and interact with their environment in ways impossible under weaker gravity. What struck me most was the interplay between perception and reality. An observer falling into a black hole experiences time normally, while someone watching from afar sees events stretch and slow. Two realities coexist, each consistent internally but profoundly different from the other. Studying time dilation near black holes taught me that the universe is not absolute. Space and time are flexible, interwoven, and influenced by mass and energy. Extreme gravity exposes the malleability of reality in ways that challenge intuition and imagination. This was the 15th surprise in my study of black holes, that black holes can distort time itself, stretching and slowing it in ways that reveal the relativity of experience, the flexibility of space-time, and the profound difference between perception and absolute reality. And in understanding this, I realized that time is not a constant river, but a dynamic fabric that the universe can bend, stretch, and shape. Before studying black holes, I imagined the universe as silent, a vast emptiness where events happened without leaving a trace unless light or matter carried information. I assumed that most phenomena were observable only through radiation, heat, or light. What surprised me was learning that black holes can create what scientists call gravitational echoes, subtle ripples in space-time that persist long after events like mergers or disruptions. These echoes are the result of extreme warping of space-time around the black hole. When two black holes collide, or when a black hole is disturbed by infalling matter, waves radiate outward, stretching and compressing the very fabric of reality. Unlike sound or light, which can be absorbed or scattered, these gravitational waves propagate nearly untouched, carrying information across billions of light years. The idea that the universe has a medium capable of ringing like a bell surprised me. Black holes, objects of darkness, can create vibrations that ripple silently through the cosmos, leaving traces detectable by incredibly sensitive instruments. What amazed me most was how these gravitational echoes reveal hidden features of black holes. By studying them, scientists can measure spin, mass, shape, and even detect subtle effects predicted by relativity. These ripples carry more than energy. They carry knowledge about the structure and dynamics of regions otherwise inaccessible. I was also surprised by how delicate these signals are. Gravitational waves distort distances by amounts smaller than the width of an atomic nucleus by the time they reach Earth. Detecting them requires instruments of extraordinary precision, like LIGO and Virgo, which can measure changes smaller than a fraction of a proton. Yet, despite their subtlety, these echoes are profound. They allow us to hear black holes in a way we never could with a light or sound. The universe speaks quietly but consistently through these distortions of space-time. Another surprising aspect is how enduring these echoes can be in theory. While many dissipate quickly, some disturbances in extreme conditions might leave lingering signatures, hints of events long past. In a way, black holes act like memory banks, recording aspects of cosmic history in the geometry of space itself. What struck me most was the poetic contrast. Objects that devour everything in sight can also produce signals that persist across the cosmos, carrying information outward rather than inward. Black holes are both consumers and communicators, shaping their surroundings in ways subtle, silent, and elegant. Studying gravitational echoes taught me that the universe has languages we are only beginning to understand. Light and sound are just part of the story. Space-time itself can convey events, history, and structure. Black holes act as composers in this grand symphony, their extreme gravity producing notes that resonate across space. This was the 16th surprise in my study of black holes. That black holes can produce gravitational echoes, silent yet persistent ripples in the fabric of reality, carrying information across incomprehensible distances and revealing the hidden dynamics of the cosmos. And in understanding this, I realized that even in darkness, the universe leaves whispers of its history, waiting for those who know how to listen. Before studying black holes, I imagined them as isolated objects, cosmic curiosities that affected only their immediate surroundings. I thought of them as predators feeding quietly on nearby stars or gas without wider influence. What surprised me was learning how profoundly black holes can shape entire galaxies. Supermassive black holes, millions or billions of times the mass of the Sun, reside at the centers of most galaxies. Their gravity anchors stars, gas and dust, influencing orbital patterns across vast distances. But their impact goes beyond gravity. When actively accreting matter, they can emit energy, radiation and jets powerful enough to regulate star formation throughout the galaxy. This dual role amazed me. Black holes are not just consumers, they are cosmic regulators, controlling the pace and pattern of galactic evolution. Too much energy can blow gas away, suppressing new stars. Too little, and stars form unchecked. Black holes act like thermostats for galaxies, balancing creation and destruction. What surprised me most was the scale of their influence. A single supermassive black hole, though tiny compared to the galaxy it inhabits, can impact regions thousands of light years away. Its presence can determine whether a galaxy thrives with star formation or becomes quiet and dormant. I was also surprised by the subtlety of the process. This influence is not always dramatic or visible. Often it manifests over millions of years through heating, radiation pressure, and redistribution of matter. It is a slow but relentless shaping of the cosmic environment. Another surprising aspect is how these interactions link the micro with the macro. The dynamics of gas near the event horizon, the properties of accretion disks, and the emission of jets can collectively influence the entire galaxy. Small-scale physics translates into large-scale cosmic architecture. Studying this made me realize that black holes are not merely endpoints of matter. They are central players in cosmic history. Their growth, activity, and energy output are intertwined with the formation of stars, the shape of galaxies, and even the evolution of galactic clusters. What amazed me most was how much we can learn from observing them. By measuring the mass and spin of central black holes, astronomers can infer the past activity of galaxies, reconstructing histories that span billions of years. Black holes serve as cosmic historians, preserving clues about galactic life cycles. This was the 17th surprise in my study of black holes, that these seemingly small dark objects at the centers of galaxies can influence structure, star formation, and evolution across enormous scales, acting as both regulators and historians of the cosmos. And in understanding this, I realized that black holes are not merely isolated consumers of matter. They are architects of galaxies, shaping the universe in ways both subtle and profound. Before studying black holes, I thought of them primarily as destructive forces, dark, mysterious objects that consume everything nearby. I admired their power, but assumed their lessons were limited to extremes of gravity and matter. What surprised me most was how much black holes can teach us about the universe itself. By studying their behavior, we gain insights into space-time, relativity, quantum mechanics, and even the early universe. Black holes act as natural laboratories, pushing physics to its limits and revealing the laws that govern reality. They force us to confront questions that cannot be answered through ordinary observations. The extreme conditions near black holes highlight the interplay between the very large and the very small. General relativity describes their gravity, while quantum mechanics hints at how particles and energy behave near the event horizon. Reconciling these two frameworks is one of the greatest challenges in modern physics, and black holes are at the heart of that pursuit. What surprised me most was how black holes also teach us humility. Despite centuries of observation, some of their behavior remains mysterious. Phenomena like Hawking radiation, information paradoxes, and gravitational waves remind us that the universe is far more complex than our intuition allows. Black holes are windows into the unknown, prompting curiosity and deeper understanding. I was also amazed by their role as cosmic messengers. The light, X-rays, and gravitational waves associated with black holes carry information across billions of light years. They allow us to study regions of space that would otherwise be inaccessible, revealing the structure and evolution of galaxies, stars, and space-time itself. Another surprising lesson is philosophical. Black holes challenge our notions of permanence, boundaries, and time. They demonstrate that the universe is dynamic, flexible, and interconnected, with even the darkest regions shaping reality in subtle and profound ways. Studying black holes taught me patience and perspective. Many of the processes involved take millions or billions of years, yet their effects are measurable. Observing, analyzing, and understanding these phenomena requires long-term dedication. but the rewards are immense. Insights into the fundamental nature of existence itself. What amazed me most was how black holes unite science and wonder. They are not only objects of study, but symbols of the universe's complexity, beauty, and mystery. They remind us that learning is an endless journey, and that even in darkness, there is knowledge waiting to be discovered. This was the 18th and final surprise in my study of black holes, that they are not merely destructive or isolated, but teachers of physics, philosophy, and cosmic perspective, revealing truths about the universe that are as profound as they are humbling. And in understanding black holes, I realized something extraordinary. That curiosity, persistence, and imagination can illuminate even the darkest corners of reality, allowing us to explore, question, and marvel at the universe we inhabit.